So when you run a correlation in something like SPSS or the software we're going to use, Jamovi, you always get a test of statistical significance thrown in. So that's a printout from SPSS. So there's correlation coefficient there, and that's the p-value, the test of significance there, and that's the sample size below it. Significance level. So what is this significance test? So this significance test is actually a t-test, and the t-test is a check to see whether the correlation coefficient is significantly different from 0. So that is this minus 0.175 in this particular example, is that significantly different from 0 or not? So we need this significance test because we're generally only estimating our correlation of interest by sampling. So that is, when we look at a correlation, what we're actually trying to find is a correlation of the entire population. So it might be the entire population of the world or whatever, but we're only testing, usually only testing a couple of hundred people. So we're just taking a tiny random sample of the overall population we're interested in, and hence we need to test that statistical significance. So in your own words, what is the significance test you get when you run a correlation, and what specifically is it telling you about the correlation coefficient? So the significance test is a t-test, and it's telling you whether your correlation is significantly different from 0. Right, true or false? We use a t-test to determine whether a correlation coefficient is significantly different from 0. That would be true. So why is the correlation between two variables in a typical behavioural study only an estimate? Generally in psychology, we're interested in how much two measures correlate in general. So across the whatever entire population that we're interested in, it could be all people in Australia or even all people on Earth, and usually that's far more people than we can actually recruit into our sample. Okay, so let's imagine that we're trying to create a measure of surgeon competency. We're going to evaluate our new test of surgeon competency by recruiting 50 surgeons to see if it can predict how good their patient outcomes are. First of all, we get them to do our test. Maybe this test might involve some sort of simulated surgical tasks, and then we follow them up and try and find out some real-world patient outcomes for each of the surgeons, controlled for whatever things we need to control for, and we correlate this with the test score, just like we did with the electricians. Okay, so let's imagine that the correlation between the test score and patient outcome rating in this case is 0.7. So our measure looks pretty good. It looks like our test can predict surgeon competency. Okay, but that's the correlation for our 50 participants. That's not actually what we want to know. What we want to know is what that correlation would be for all surgeons who have ever lived, including people who are not yet surgeons but might be in the future, and could even include people who haven't even been born yet. Well, the problem is, of course, that we just can't test every single surgeon that's out there and is yet to be. But fortunately for us, it turns out that even if we test a relatively small number of people from that population, randomly sampled, we can get a surprisingly accurate estimate of that population correlation. The example is political opinion polls. So political opinion polls are generally only sampling about maybe 1,500 people, but sort of randomly chosen to be representative of the general voting public. And this, despite people moaning and groaning about these things, they're actually surprisingly accurate at predicting actual election results. Let's say a sample of 1,500 voters gets it right within plus or minus 3% of what the actual results are when you actually survey the entire population when you actually run your election. We can be pretty confident our estimate of 0.7 from 50 people is going to be a reasonable approximation of the true population correlation. Okay, so there's a marginal error in this figure, and that marginal error generally gets smaller the more people we include in our testing sample. In your own words, a national poll of 1,500 people is published showing Labour is 1 point ahead of the coalition. A journalist says that Labour is now in the lead. Okay, explain to them why they can't necessarily conclude this. The answer to that is that probably a 1 point advantage from a poll of 1,500 people is within this error margin of plus or minus 3%. So the idea is that essentially means that that 1 point advantage is not statistically reliable. So the idea is it's within that margin of error. You can't say that Labour is in the lead from that sort of result. How can we draw conclusions about entire populations based on relatively small samples? And the answer to that is just the sort of stuff I've said on this slide, is that even if you can sample randomly from a population, you actually don't need a huge proportion of that population in order to get a relatively accurate estimate of the population statistics that you're after. So sample size determines the accuracy of the correlation estimate. Right. Generally, the bigger your sample, the more accurate and stable, and therefore closer to the population correlation your estimate will be. On the other hand, if you've got a really small sample, what does that mean? It means that your estimate of the population correlation will probably be pretty inaccurate, and therefore not less likely to be close to what the real population correlation is. Okay, so true or false, if we test more people when estimating a correlation coefficient, then we are likely to obtain a larger correlation. So that's false, because this, what I'm talking about on this slide, isn't about whether the correlation is going to be larger or smaller, it's whether the correlation is going to be accurate or inaccurate. It's about how close it is to the population correlation, which may be big or it may be small. So to turn that into a true statement, we can say if we test more people when estimating a correlation coefficient, then we are more likely to obtain a more accurate estimate of the population correlation.
Now let's talk about the significance test that comes with a correlation when you run it in something like Jamovi. So when you run a correlation, you'll get the correlation magnitude itself, the estimate of that based on your sample, and you'll get a p-value. And the p-value is basically telling you how likely it is that you would get a correlation this large if the real underlying population correlation was actually big fat 0. So, for example, if you obtain p-value 0.05, with a correlation coefficient of, say, 0.8, it means that if your true population correlation was 0, correlation this large or larger, you would only get it about 5% of the time due to sampling error. Okay. So, let's look at this line here. So, in the middle, we've got 0, and then +1 is the maximum correlation, -1 is the lowest correlation. So, let's say, so our null hypothesis is that the underlying population correlation is 0. Now let's say we've actually collect our data, but our data is only from a small sample of the overall population. And so let's say we get some number up there. So what's that? Yeah, 0.6, 0.8, something big. The question is, could the difference that we're seeing there have arisen through chance? That is, the real correlation isn't the 0.8 that we're seeing, it's actually a big fat 0. What's the chances of that? And essentially that's the question the significance test is answering. It's saying, is the sample correlation sufficiently different from 0 that sampling error alone is unlikely to explain that observed result? I.e., if the p-value significantly is substantially small, then we can say, well, that probably is a real correlation here, rather than the correlation being a big fat 0. True or false? The significance test you get with a correlation coefficient tells you whether it is significantly associated with 0. That is false. Okay, so the significance test is more telling you whether the correlation coefficient you're seeing from your sample is significantly different from 0.
So, if we've got a super large correlation, then it's much easier to detect it as being different from 0 because we don't need quite so much sensitivity. Because we're way away from 0, we can get away with smaller sample sizes because the difference we're trying to evaluate is much bigger. Okay. On the other hand, if you've got a really small correlation, something that's much closer to 0, we need much more sensitivity to be able to discriminate it from 0, i.e. we need to test a much larger sample. Okay, so in your own words, what factors affect whether a correlation is going to be statistically significant or not? So those factors include your sample size and the magnitude of your correlation. Now let's talk about margin of error and correlation coefficients. Okay, so when we are estimating our correlation using a sample, okay, and in this case here it's a small sample, relatively small number of people, we're using to try and estimate what would be the population correlation if we tested everybody in the whole world. And the thing with a small sample is that it's quite inaccurate. That is, we get quite a big margin of error associated with it. Okay, so that estimate is inaccurate, it's got a large margin of error. Okay, and the more people we test, the more accurate the estimate, therefore the smaller the margin of error. So in your own words, what's the relationship between a correlation coefficient's margin of error and the sample size? Basically, the bigger your sample size, the smaller the margin of error will be. Let's say our population correlation, if we test everybody in the world, is there. Okay, so now we've tested a huge number of people, much larger sample. The effect that's had is that our margin of error here is much smaller, therefore our estimate's going to be much closer to the real correlation, the population correlation. Okay, so much more accurate with a smaller margin of error, smaller confidence interval, as we say. Okay, true or false, the confidence interval associated with a correlation coefficient decreases as the sample size increases. So that's true. Okay, so that's essentially saying the margin of error associated with a correlation coefficient estimate gets smaller and smaller and smaller the bigger your sample size is, because it's getting more accurate. The smaller the sample size, the greater the precision that our correlation coefficient will have. So that's false, because small means it's there's more imprecision, it's less accurate. Okay. Third one, correlation coefficient will be more likely to be closer to the population correlation if the sample is larger, so that's true. Bigger the sample size, then the more accurately we're estimating that population correlation. Right, so this is a situation where our population correlation happens to be very close to 0, but it's not quite 0. Okay, so it's close to 0. Then the problem is, if we only have a small sample, then it's going to, with a large margin of error, then that large margin of error is likely to include 0. That is, we won't be able to tell apart our correlation from 0 because of the large margin of error. Okay, so essentially that means that our correlation won't be significant. We can't conclude that the population correlation is likely to be greater than 0, even though in reality it is, but it's just very close to 0. True or false, when the population correlation is close to 0, i.e. small, then we'll probably need an enormous sample to be able to get a correlation coefficient that is significantly greater than 0. So that's true. So the idea is that when we're that close to 0, the margin of error needs to be tiny to be able to discriminate it from 0, so that it doesn't that margin of error doesn't include 0. And to get that margin of error that small, we need a big sample. In your own words, explain in terms of sampling error why we need larger samples to be able to get significant correlations when we're expecting small effect sizes. Okay, so essentially that's what we're looking at in this slide. So the thing with a small effect size is that it's very close to zero. When it's very close to zero, we need very accurate estimates of our correlation in order to distinguish it from zero, because the margin of error, we want the margin of error to not include zero. Okay, and when it's very close to zero, the margin of error has to be very tiny to not include zero. Okay, so here's our population correlation, which is close to zero. But this time what we've done is tested loads and loads and loads of people. That's given us a very small margin of error, and hence we're able to detect that our correlation estimate as being significantly different from zero, even though it's small. Right, so this is the opposite situation when our population correlation is very close to 1. That's it. It's a very, very big effect size. It's a very strong correlation. It's a big relationship between the two, whatever the two variables are we're looking at. Okay, so in this situation, even if we have a pretty small sample size with a big margin of error, we will get a significant result because it's so far away from zero. Okay, as you can see there. So the idea is margin of error is large, it's unlikely to include the 0 point, therefore we can get it as being significant. Alright, so let's look at the questions. True or false? When the population correlation is close to 1, then we'll probably need an enormous sample to be able to get a correlation coefficient that is significantly greater than 0. So that's false. We actually can get away with quite a small sample if to get a significant result there. Because we're so far from 0, we can tolerate a large margin of error. In your own words, explain in terms of sampling error why small samples might be sufficient for finding significant correlations when we're expecting large effect sizes. Okay, so that's just what we're illustrating on this slide here, where even with small samples we give ourselves big margin of error, but because when we're expecting very large effect sizes, we're miles away from 0, we can put up with a large margin of error, and therefore it's okay to have a small sample in this sort of situation, just in the terms of getting a significant effect. That doesn't necessarily mean that when we've got a really big correlation, a correlation that's close to 1, that there's literally no point in getting a very large sample. So it still might be useful to test lots of people in this situation, because we still are getting a more accurate estimate of what the population correlation actually is, because we've reduced that margin of error. Okay, so we don't need the large sample to get statistical significance, but we still might want a large sample just to get a better estimate of the exact value of that magnitude of that correlation coefficient. So a correlation can be strong and yet not significant if we test a tiny number of people, but a correlation can be weak but significant if we test hundreds of people. Okay, true or false? If we're expecting a certain population correlation to be large, then there would never be any point in sampling more than a small number of people when we attempt to estimate it, and so that's false, because there might be a situation where it's not just about getting the thing significant, it's also about knowing to some degree of accuracy what the magnitude actually is, not just that it's miles away from 0. In your own words, explain to Muggle why only knowing the statistical significance of a correlation coefficient would never give the full picture of what is going on. Okay, that's because the statistical significance is only telling you one element of the story, which is whether your correlation estimate is significantly different from 0, and that is dependent not only on the size of the correlation, it's also dependent on the sample size. We'd also need to know the correlation coefficient itself, because it could just be that it's significant because you've got a large sample size even though the correlation is pretty close to 0, as in it's a pretty weak relationship, or maybe it could be that you've got a small sample size and it's significant, but we get away with it being significant because the underlying correlation is enormous. Knowing the statistical significance doesn't give you the full picture. We also want to know the correlation coefficient. And for the real, of course, full picture, we want to look at the scatter plot and all that sort of stuff as well. Practical upshot of all of this stuff is that we need to be quite careful when we choose what sample size we're going to use in our study. So our choice of sample size will depend on how big we expect the correlation that we're looking for to be. Okay, maybe we estimate this by looking at previous research, for example. And in fact, we can be sort of quite systematic about this by using a technique that hopefully you've come across, which is called power analysis. And power analysis basically tells you exactly how many people you need to test to be able to detect a particular size of correlation as significant. In fact, power analysis, it's not just restricted to correlations. You can use it for pretty much any statistical test. Okay, but we're just talking about correlations here. And in fact, we can sum it up with this table here, where you can work this all out with software, or you can work it all out using equations, but we're just going to keep life simple for ourselves here and do it the simplest way, which is just to look it up on a table where someone's done all the calculations for us. To give an 80% chance, so 80% we're just going to say that's a reasonable chance of detecting these particular correlations as being significant at the 5% level, we need the following numbers of people. So for a large correlation, which is has been historically defined as a 0.5 correlation, we need 28 people in our sample. To detect a medium-sized correlation, historically a 0.3 correlation is classed as medium, we need 85 people. But to get a small correlation, that's 0.1, we need nearly 800 people. So you can see it sort of jumps up substantially the closer you get to 0. And if you're doing further research and you need to look into this sort of thing in a bit more detail, a good first starting point is this reference here by Cohen, which is one of the classic seminal works on power, which has tables for not only correlations but for a lot of the other common statistical tests that we might use. But for the purposes of this course, it's fine just to stick with what I've shown you here. So, true or false? Power analysis can tell you how many people you need to test in order to guarantee that you would find a statistically significant correlation coefficient. So that's false because of the word guarantee. Power analysis doesn't guarantee you'll get a statistically significant correlation because we're just dealing with probabilities here. It just tells you what your chances of getting a statistically significant correlation are. So there are no guarantees in statistics. Second question. If we want to be able to detect a small correlation as being statistically significant, then we'll probably need to test hundreds of people. Yes. So literally, if we want to detect a small correlation being statistically significant and we're happy with our 80% chance, in fact we'd need about 800 people to detect a 0.1 correlation, looking at that table. Question 3. We have a reasonable chance of detecting a large correlation as being statistically significant if we only test 30 people. So looking at that table, yeah, that's true. Okay, so 30 people is considered sufficient to have a 80% chance of detecting a 0.5 correlation as being statistically significant. In your own words, what is power analysis? So, yeah, all you have to say for that is it's a technique that allows us to estimate the sample sizes we need to test to be able to detect a particular effect size as being statistically significant. Right, let's now talk about practical importance as opposed to statistical significance for correlations. So, just because a correlation turns out as statistically significant doesn't mean that it's necessarily practically important. Okay, and here's a little example for you. You're a clinical psychologist and you want to see whether the number of hours spent participating in some clinical intervention is correlated with depression levels after that intervention. So presumably this is an intervention to reduce depression. So we test 1,000 people. Okay, by the way, that's a ridiculously large number of people for a clinical study like this. We test 1,000 people and we find a correlation of minus 0.15 between hours spent in the intervention and depression level. So more hours, less depression. On the face of it, that's what we want. Okay, and that turns out to be statistically significant because we've got such a large sample size. Are we going to be happy with that? So no, probably, because the effect size, it is significant, but it's pretty tiny. It's a small effect size. Okay, so that is, in practical terms, what we're trying to say here is it a good sort of use of money to use this particular clinical intervention? Well, this is suggesting that, actually spending more time in this particular intervention, it's got a real effect. It seems to reduce depression levels, but that reduction seems to be pretty trivial, pretty small. So that intervention is probably a dud, even though it's reducing depression, but is it good value for money? Probably not. True or false? If a correlation coefficient is statistically significant, then it is very likely to be of practical importance, so that's false. So it's the case that, it could well be, we could get something that's statistically significant, but that doesn't necessarily mean that it's something that we would then want to use in the real world if we're talking about a validity of some test or some intervention. Right. Note the actual level of correlation, considered important or not important, is extremely context dependent. So it's not the case that I can give you some sort of rule of thumb for, like 0.5 correlation is good and 0.1 correlation is bad. It depends entirely on the context. Okay, and usually in clinical psychology, when we talk about this practical importance, we refer to this as clinical significance to differentiate it from statistical significance. In your own words, what's the difference between clinical significance and statistical significance? So the difference is clinical significance is whether the effect size you're getting is likely to have a clinically meaningful effect. Is it something that you actually want to go ahead and use this intervention or this test in a clinical setting because of the effect size is big enough? That's clinical significance. Statistical significance is, if we're talking about a correlation, is that correlation significantly different from zero? And that's affected by how big the correlation is, but also by the sample size in your study. Alright. So likewise, if a validity coefficient, so in that last example we were talking about an actual intervention, okay, now we're talking about tests. If a validity coefficient, a correlation between a test score and some criteria that that test is supposed to be measuring, as we saw in those previous examples with electricians and surgeons, if that validity coefficient is significant, this doesn't necessarily mean that that test is therefore valid. All it means is that the correlation between the test and the criterion measure is significantly different from zero. Okay, so again, just reiterating that the significance level doesn't tell you how big the correlation is because it's also dependent on the sample size. Of course, you can get very small correlations that are nonetheless statistically significant if you've got sufficiently large numbers of people. Alright, so if a correlation coefficient is not statistically significant, then what can we say? Well, we can't be sure in this case whether the real population correlation is actually greater than zero. So this is a situation if a correlation magnitude is large, so that is we do our study and, for example, our test score and its criterion now have got a very high correlation between the two. That means nothing if it's not significant. Even if the correlation magnitude is large, a lack of significance means our estimate must be so inaccurate that we still can't conclude that the real correlation, the population correlation, is not zero. Alright, true or false? If the validity coefficient for a criterion measure is statistically significant, then this does not necessarily indicate that the test is valid. Okay, so that's true. Okay, so it may indicate the test is valid, but it may not. It could just be that you've got that statistical significance by having an enormous sample, but the actual effect there is so small that your test isn't really measuring the criterion very well. Question 2, if a correlation coefficient is large enough to be of practical importance, then it's not necessary for it to be statistically significant. So that's false, in that because if it's large but it's still not statistically significant, it means that estimate you've got there must be incredibly inaccurate. So it could be that the population correlation is actually still zero. You can't tell.
So there are lots of different types of correlation, but I've chosen to focus in on these two very useful and important ones. First one is Pearson's R. So Pearson's R is a parametric correlation, and that means that it has stricter assumptions behind it. So for the purposes of this course, we're going to say that the variables we put into this must be approximately normally distributed, and we're going to say those variables must be on an interval or ratio scale of measurement. Note that if you want it to be sort of strictly accurate in statistical terms, these assumptions are sort of like approximations, sort of rough and ready things that allow us to make a decision. But if you talk to a statistician, they'd be telling you, actually the reality behind it's much more complicated, but we are not going to go into that in this course. Okay, so if possible, we would like to do our Pearson's R, because being parametric, that means it is a more sensitive measure of your correlation, because it's using more of your data. So the other correlation coefficient we're going to look at is called Spearman's rho, and this is the non-parametric version of Pearson's R, and that means it doesn't have all of those assumptions. So the variables can be normal, but the point is they don't need to be normally distributed. And we can analyze things that are on the ordinal scale of measurement as well as the interval ratio scale. Okay, so if the Spearman's rho can be used in every situation that Pearson's R can be, why don't we just use Spearman's rho all the time? And the answer is that it is less sensitive than Pearson's R. So Spearman's rho is only using the rank order of your data rather than looking at the raw scores and the differences between them and that sort of thing. So it's using less of that information from your raw data, but it's more robust in terms of its assumptions. So in terms of our general sort of process for deciding which one to use, if when you're looking at your data, you discover they are appropriate for a parametric test, assuming normal distributions and so on, then we'll use Pearson's R. If that's not the case, where let's say the data isn't normally distributed, then we're going to try and make that distribution normal by applying nonlinear transformations to it, and we'll tell you how to do that later in the course. But if we do our nonlinear transformations and we can't make the distribution normal with them, then we would use our non-parametric Spearman's rho instead. So the Spearman's rho is our backup plan if we can't meet the assumptions for the Pearson's R. True or false? Spearman's rho is a type of correlation coefficient appropriate for use on nominal data. So that is false. So we can use it on ordinal data, we can use it on interval data or ratio data, but we can't use it on nominal data. Question 2. If you had two variables that were both on the interval scale of measurement, then you could potentially use Spearman's rho to evaluate the correlation between them. That is true. So you can use Spearman's rho to look at any any correlation that you would have used for Spearman's R. It's just not quite as sensitive. So that's why we want to use Pearson's R if we can. Question 3. If you had two normally distributed variables that were both on the interval scale of measurement, then you could use Spearman's rho to evaluate the correlation between them. True. for the reason I just gave, is that, just because that's a situation where we can use Pearson's R, it doesn't mean it's wrong to use Pearson's Rho. It's a Spearman's Rho, rather. It's just that Spearman's Rho is less sensitive, so we prefer to use Pearson's R, which is using more of our data.